In this video, we're going to go over some practice problems on the material covered this week. And so we'll start with section 7.5 here. So in these first two questions, what we want to do is simplify each product. So for question 8 here, we're simplifying the square root of 10 times this binomial in our parentheses here. So in this case, we can use our distributive property that we're pretty comfortable with here. This square root 10 is going to be distributed to both terms inside of our parentheses here. We're going to end up with the square root of 10 times 5 plus the square root of 10 times the square root of 3. All right, so fully simplifying this, we'll write our first term as 5 times square root of 10, like that there. And then we have the square root of 10 times the square root of 3. Since these guys have the same square root here, we can just multiply these guys under our square root. So this would be the square root of 10 times 3, which is the square root of 30. Now remember, we can only do this if we have the same root. So if this was the third root of 10 times the square root of 3, we would not be able to multiply them in this way, but since they're both the square root, we can. So this would be our final answer for this one here. Now for this next question here, we're going to multiply these two binomials here, and these binomials both have radical terms here. Now in order to do this, we're just going to use our FOIL method that we're pretty comfortable with. We're going to multiply our first, outer, inner, and last terms together. So let's break this down here. We're going to have the square root of 8 times the square root of 8. That's going to be our first multiplication here. Then we're going to have the square root of 8 times the square root of 2 here. So this will be our second term. And then our third term is minus square root of 2 times square root of 8. And then our last term here is minus square root of 2 times positive square root of 2. So this would give us a negative root 2 times root 2 here. All right, so let's simplify this even further. We have the square root of 8 times the square root of 8. And again, we have that both of these are square roots, so they can go under one radical. This will be the square root of 8 times 8, which is 64. Now notice our next term is the square root of 8 times the square root of 2. And then our third term here is the opposite of that. We have negative square root of 8 times the square root of 2. So these guys are actually going to cancel each other out. And then our last term here, again, we have the square root of both of these guys, so we can multiply them under one radical symbol here. So this would be minus the square root of 2 times 2, which is the square root of 4. Now, taking the square root of both of these guys, the square root of 64 is 8, and the square root of 4 is 2. So in this case, our final answer is going to be 6. Now, looking at this example here, I just wanted to point out that this term here, or this guy here in this binomial, is what's called the conjugate of this one. And we'll touch on that a little bit more in the next, or in a couple examples here. But essentially, the conjugate of a term here is, for example, if we have the difference of these two terms, the conjugate is going to be the sum of those two terms, and vice versa. If we have the sum of two terms, then the conjugate is going to be the difference of those guys. And we'll go, like I said, we'll go over this in the next couple examples here. So the next thing that we're going to look at in this section is called rationalizing denominators. And we do this because a simplified radical expression has no radical in the denominator. So for example here, this one is not fully simplified because we have a radical in the denominator. And so what we're going to do is we're going to simplify this by multiplying it by 1 in the form of this radical divided by itself. So what I mean here is we're going to multiply this guy by square root of 6 over the square root of 6, right? Because this guy is just 1, so when we multiply this by 1, it's not actually changing the value of this guy. Now, the reason we're doing this is because when we multiply this out, we're going to end up with a fraction that no longer has a square root in the denominator, and therefore it would be fully simplified. So let's go ahead and do this. In the numerator, we have 12 times the square root of 6. And in the denominator here, we have the square root of 6 times the square root of 6. Well, since these guys are the same nth root here, we can just write them under one radical expression. It'll be the square root of 6 times 6, which is 36. Now, in the numerator here, let's keep this. We have 12 times the square root of 6. We can't simplify that guy. But in the denominator here, we have the square root of 36, which we know is just going to be 6. So by multiplying this here by the square root of 6, we ended up with the square root of our perfect square here and getting rid of a square root in our denominator. Now from here, we can still simplify this a little bit further. We have a factor of 6 and 6 here, so we're just going to be left with 2 times square root of 6 in the numerator and 1 in the denominator. So this will be 2 times the square root of 6. So that is how we would rationalize the denominator for this guy. Let's look at another example here, question 67. This is going to be the same thing as negative square root of 48k squared over the square root of z. So as we can see, this is not a fully simplified radical expression because we have this square root in the denominator here. So what we're going to do is multiply by a factor of 1 of this form here, or not a factor of 1, we're multiplying by 1, which is of this form here, square root of z over the square root of z. We're going to do this because, again, this is going to get rid of the square root in the denominator as we saw in the last question. So what happens here is we're going to get negative square root of 48k squared times the square root of z. And in the denominator here, we're going to get the square root of z times z, all under one square root. Z times z is z squared. And since we're taking the square root of that, we're just going to end up with z in the denominator. So what I mean is we're going to have the square root of z squared. Now, these guys are going to cancel our squared and our square root, so we're just going to end up with z in the denominator. Now, that won't be our final answer though. We can simplify this a little bit further. So what we're going to try to do is rewrite the square root of 48 and k squared and break them up into their factors. So we know that 48 is the same thing as 16 times 3. And so this will be 4 times 4 times 3 here. So we can break that up into those factors there. So we're going to be left with, in the numerator, the square root of, I guess we could just write this as the square root of 16 times the square root of 3. Yeah, let's write it this way here. You could do it either way, you'd end up with the same answer. Then we have the square root of k squared and the square root of z. So that's all in the numerator here. This is the same thing as the square root of 48, and then we have the square root of k squared here. Now in the denominator, we just have z since we rationalized it. Then in the numerator, this is going to give us the square root of 16, so that'll give us 4. Then we also have the square root of k squared, so this will just give us k by itself. And we can't simplify the square root of 3 or the square root of z here, but what we can do is rewrite them under one radical. Since they're both square roots here, we can multiply them under the same radical expression. And so this is going to be all over z here. So that would be our final answer. We can't simplify this any further. So that's how we would rationalize this denominator and simplify this guy. Alright, so for this next example, we're going to do something similar, except now we're dealing with a third root instead of a square root here. So we're going to rewrite this as we have the third root of x raised to the 6th power over the third root of y. Now in this last example here, what we did was we immediately multiplied by the square root of this guy to the numerator and denominator of this fraction here. Then, after we got rid of the radical in our denominator, we simplified the numerator. In this example here, what we're going to do is simplify the numerator first, and this is just to emphasize that you can do it either way. So before we try to rationalize this denominator here, let's first simplify the numerator if possible, and in this case it is possible. We can split up x raised to the 6th power into two factors. This would be x cubed times x cubed. Remember our exponent rules here. If we're multiplying x cubed times x cubed, this is the same thing as adding their exponents here. So we're going to have that in the numerator. And our product rule tells us this is the same thing as the third root of x times the third root of x. So we're just going to end up with x times x in the numerator. So this would be x squared in our numerator. And then in our denominator, we still have this guy. So now what we're going to do then is we're going to multiply this whole fraction here by 1 in a certain form here so that we can get rid of this third root. Now, in the past, what we did was we multiplied, as you can see here, we multiplied by exactly what we had in the denominator because we know that we're going to end up with, for example, here, z times z, which gives us z squared, and then we can take the square root of that. Now, in this case here, if I were to multiply this, let's see, if we were to multiply this by the third root of y over the third root of y here, when we multiply these two guys, we're just going to end up with the third root of y squared. And that wouldn't really help us. We wouldn't be able to simplify anything here. So we have to be a little clever with what we want to multiply this by to get rid of our radical. So instead of multiplying by that, instead let's multiply by the third root of y squared. And we'll see why in a moment. Doing this, we're going to end up with x squared times the third root of y squared over, well, we have the third root of y times the third root of y squared. Since these guys have the same root power here, we're just going to multiply y times y squared under our third root. Doing that, we're going to end up with the third root of y times y squared, which is y cubed. So now you can see why we chose to multiply by this instead of just the third root of y. These guys here are going to cancel, and we just end up with y in our denominator. So we're going to have x squared times the third root of y squared in our numerator over y. Now we can't simplify this any further. This is our final answer here, and we know it's our final answer because we no longer have a radical in the denominator. All right, so let's move on to question 87 here. So again, we're going to have to rationalize this because we have a radical in our denominator, so this is not fully simplified. But in this case, we have a binomial expression in our denominator. So far, we've only dealt with one term in our denominator here, so we only needed to multiply by one term in the numerator and denominator here. So in this case, this brings us back to our idea of conjugates. This is what I talked about in example 19 here. These two guys are conjugates of each other. In fact, if we have something of the form x plus y, its conjugate would be x minus y. So, as we saw in example 19 here, when we multiplied by the conjugate, a bunch of terms canceled. So what we're going to want to do, we ended up with a number that did not have a radical. We ended up with just 6 in this case. So what we're going to want to do is something similar here, because when we multiply by the conjugate, that gives us an indication that we're going to get rid of radical expressions. So let's do that in this case. The conjugate of 3 minus root 2 then would be 3 plus root 2. So from here, we're going to have to FOIL this. In the numerator, we'll just have the square root of 8 times both of these terms here. So we're going to have 3 times the square root of 8, and then we're going to have the square root of 8 times the square root of 2. So we can write this, actually let's do this step by step here. We have that there. Now in the denominator, we're going to have to FOIL this. So our first term is going to be 3 times 3. This will be 9. Our second term is going to be 3 times root 2. So this will be 3 root 2. Our third term then is minus root 2 times 3. So that'll give us a negative 3 root 2. Then our last term here is minus root 2 times plus root 2. So this will give us negative. This will give us minus root 2 times root 2. Running out of room there. Okay, so from here, let's simplify this. In our numerator, we have 3 times, this is going to be the square root of 4 times 2, just splitting this radical up. And then the second term here, we have 2 times 8 under our square root. So this would be the square root of 16. In our denominator, we have positive 3 root 2 minus 3 root 2. So these guys are going to cancel. And so we're just left with 9 minus, we have root 2 times root 2, which is going to be the square root of 4. All right, so let's keep simplifying this here. For this first term, we have 3 times the square root of 2. So that'll be, or sorry, 3 times the square root of 4, which gives us 2 times root 2. Then we have the square root of 16, which is 4 over 9 minus the square root of 4. So our final answer then would be 6 root 2 plus 4 in our numerator, and then 7 in our denominator. So we can't simplify this any further, and we know that this is fully simplified since we don't have a radical in our denominator. So for the last example in this section here, we want to write this quotient in lowest terms. So we're going to fully simplify this guy. Now the first step to doing so is notice that this first term and the second term here both share a factor of 10. So let's pull out this factor from both terms here. So we're going to be left with 3 plus 2 root 6 in the numerator, and in the denominator here we have 10. So these 10s here can cancel, and then we're just left with 3 plus 2 root 6. And so this will be our final answer here. All right, so in section 7.6, we're going to be solving equations with radicals, and we're going to do so using this property here. Now, this says that if we square a square root here, these guys essentially undo each other, and we're just left with whatever's under our square root. So let's look at this first example here. We want to solve this equation here, so we want to completely isolate our variable k. Now to do that, the first thing that we're going to do is we're going to subtract 2 on both sides here. We're left with the square root of 5k minus 3 is going to be equal to negative 2. In fact, whenever we're solving equations with radicals, we do usually want to get the radical by itself on one side of the equation and everything else on the other side. This is because we want to use this property here. So we want to square root both sides to get rid of our radical. Now, if we were to square root both sides of our equation in this form here, before we subtracted 2 on both sides, this would get very messy. So, in this case here, our square root and our power 2 here are going to cancel each other out. So we're just left with 5k minus 3 on the left-hand side of our equation. Now on the right-hand side here, we're going to be left with 4. Now this becomes a pretty easy equation to solve. We're going to add 3 on both sides. We're going to be left with 5k is equal to 7. And then we're going to divide by 5 on both sides to completely isolate our variable k. So k is going to be equal to 7 over 5. Now, something to note here, when we use this property, this is called the power rule here for solving a radical equation. When we use this property, it says that what we're doing is we're squaring both sides of this equation. And it says that if both sides of an equation are raised to the same power, like we did in this case here, all solutions of the original equation are also solutions of this new equation here. However, this power rule does not say that all solutions of the new equation actually are solutions. They could or couldn't be. So this solution here, this 7 over 5, is actually what's called a proposed solution. So whenever we're using this property here, or this power rule, what we have to do is check that this is in fact a solution. We have to do this every single time we use the power rule. So what we're going to do, let's move this over actually. We're going to check this proposed solution. So in order to check it, we're going to plug this value for k into our original equation. And if this statement holds true after plugging k in, then we know that it will be a solution. So we're going to end up with, if we plug k into this guy here, we're going to end up with 5 times 7 over 5. So the 5s are going to cancel. And we're just left with 7 here. Then we still have this minus 3 in our radical, and plus 2 is going to give us 0. So we're going to end up with the square root of 4 plus 2 is going to give us 0, and this is not true. So this actually is not a solution. So in this case, our solution set is going to be the empty set. We don't have a solution for this guy. All right, let's look at another example here. Again, we're going to use our power rule. So we're going to we're going to square both sides of our equations here to get rid of that square root. So we're going to square this side and this side here. So doing that, we're going to write it over here so we have room to check our answer. We're going to end up, we know that this square is going to apply to this 2 and this square root here. So we're going to end up with 2 squared, and then we're going to have the square root of x squared. So just emphasizing that that 2 is getting distributed to both of those guys. Then on the right-hand side, this radical is going to cancel with this guy, so we're just left with 3x plus 4. So simplifying the left-hand side here, we're going to end up with 4x is going to be equal to 3x plus 4. Now we can easily solve this guy. Let's move our x's over. Doing that, we're just going to end up with x is equal to 4. Now again, we're going to want to check this. This is a proposed solution. So let's plug this value for x into our original equation here. So if we're to plug 4 into this guy here, this would be the square root of 4, which is 2 times 2. So that'll give me 4 on the left-hand side. Now on the right-hand side here, I'm going to have 3 times 4. So this will be 12 plus 4. So that'll be the square root of 12 plus 4, which is the square root of 16. And we know that the square root of 16 is in fact 4. So this is a true statement. So this means this proposed solution is a solution. So our solution set is going to be x is equal to 4 in this case. All right, let's look at another example here, 27. Now in this case here, we have that our radical is by itself on one side of our equation, so we can go ahead and square this right away. Whatever we do to one side, we have to do to the other, and this is where it gets a little tricky. So far, we've only been squaring single terms here, but now we're going to be squaring a binomial. So what we're going to have in this case, let's do this over here. On the left-hand side, we're going to have 9 minus x. That radical is going to go away. And on the right-hand side, we have x plus 3 squared. So what we're going to do is expand this guy. We're going to FOIL it. We're going to be left with, on the right-hand side, foiling this guy, we're going to get x squared plus 3x plus 3x, so that'll be 6x, plus 3 times 3, which gives us 9. So now we're just going to solve for x. The first thing that we'll do, since we have a quadratic equation here, let's try to get that this is equal to 0 and use our zero factor property. So we're going to add x to both sides, and then we're going to subtract 9 to both sides so that we're going to get 0 on one side of our equation. We're going to end up with x squared plus 7x, and then these 9's here are actually going to cancel. So we're just going to have x squared plus 7x is equal to 0. Now from here, we can use our zero factor property by first factoring this guy. We're going to get x times x plus 7 is equal to 0. So this means either x is equal to 0 or x plus 7 is equal to 0 or both. So this tells us our two proposed solutions are x is equal to 0 or x is equal to -7. Now again, we're going to have to check this guy. So we're going to plug in these values into our original equation. For x is equal to 0, we're just going to get the square root of 9 on the left-hand side and then 3 on the right-hand side. So that is a true statement. Now for -7, if we plug in -7 into our x here, we're going to get 9 plus 7. So this will be the square root of 15 on the left-hand side. Now here we're going to plug in -7, so this will give us a -4 on the right-hand side, and so this guy is not true, so this is not a solution. So our only solution in this case is going to be x is equal to 0. Now for this next example, it's going to be a little trickier. Like we saw in the last several examples, it is easier if we have a radical on one side of our equation and everything else on the other, but in this case we have two radicals. We did see another example of that for question 19 here. We had two radicals on both sides of our equations, but that was fairly easy. All we had to do was square root both sides and they both canceled out. In this case here, we're going to want to do something similar. We're going to want the radicals to be on either side of our equation so that they can cancel out when we take the square. So the first thing we're going to do is we're going to move this second radical to the other side of our equation. So we're going to be left with the square root of 3x minus 2 is going to be equal to 1 plus the square root of x plus 3. Now, from here, what we're going to do is we're going to square both sides so that we can get rid of this radical here. So we're going to square this, but we're also going to square the entire right-hand side of our equation. Whatever we do to one side, we have to do to the other, and we can't just square one term. We have to square this guy as well. So what we're going to end up with on the left-hand side is just 3x minus 2. Now on the right-hand side, I don't want to run out of room, so let's do this over here. We have 1 plus the square root of x plus 3 times the same thing. So we're going to have to FOIL this guy out here. So our first term is just going to be 1. Our second term is going to be 1 times this, so just this guy. We again have this times 1, and then these two times each other. So after FOILing that out here, we're going to get 1 plus, we're going to have 2 factors of the square root of x plus 3. And then our last term here is going to be the square root of x plus 3 squared. Alright, so let's simplify this a little bit further. This is going to be 3x minus 2 is equal to 1 plus this here. Plus, we know that the square root of, the square root of x plus 3 squared is just going to give us x plus 3. Alright, so this is becoming a little bit easier to solve. Let's try moving some things around and combining like terms. So, what I can do is I can subtract x on both sides of our equation to combine those guys, and in the same step, I'm going to combine our 1 and our 3 here. Doing that, we're going to end up with 2x minus 2 on the left-hand side, and then 4 plus 2 times the square root of x plus 3 on the right-hand side here. Now we still have this radical, so we're still going to use our property here so that we can square both sides to get rid of our radical. But before we do that, let's keep this radical on this side of our equation and keep it and get it by itself. So we're going to subtract 4 on both sides. Doing that, we have 2x minus 6 is going to be equal to this guy. So we just have a radical term by itself on one side of our equation, so that's good. So now we're going to have to use this property again. We're going to square both sides. Doing that, we're going to want to FOIL this guy. We're going to have 2x minus 6 times 2x minus 6. So we're going to end up with, this will give us 4x squared for our first term. Then our second term is going to be minus 12x. And then our third term is also going to be minus 12x. So this will be minus 24x. And then our last term is going to be minus 6 times minus 6. So that'll give us plus 36. So we just get this whole thing by FOILing this guy, because it'll be 2x minus 6 times 2x minus 6. Now on the right hand side, this 2 is going to be applied to this 2 here. So this will be 4. And then we know that this 2 applying to this radical here, these guys are going to cancel out. So we're just going to have 4 times x plus 3. So we've officially gotten rid of all of our radicals here, and now we can distribute and combine like terms and try to simplify this guy. So we're going to have 4x squared minus 24x plus 36 is equal to 4x plus 12. So in the same step, I'm going to move everything to one side. Doing that, we're going to have 4x squared, and then we're also moving these guys over. So this is going to be 4x squared minus 20x plus 24 gives us 0. So now this is looking like something that we can factor. Notice that all three of these terms share a factor of 4, so let's pull that out. Doing that, we're left with a now factorable polynomial here. So this is going to be the same thing as 4 times x minus 6 times x minus 1. Now using our zero factor property, this means x is going to be equal to positive 6 or x is going to be equal to positive 1. And we're running out of room here. Let's move this up a little bit. So our proposed solutions are x is equal to positive 6 or x is equal to positive 1. Now, we don't care about this 4 here because 4 is not equal to 0 here, so this we can ignore. We're only concerned on what x values will make this whole thing equal to 0. Alright, so those are our proposed solutions, and again, we're going to have to check them. So, let's come up here, put that on the side. So our first solution that we're going to check is plugging in x is equal to 1. So, we're going to have 3 times 1 minus 2 under our square root here. So that'll just be the square root of 1. And then we're subtracting out, sorry, let's actually just plug this right in. I don't want us to lose track of what we're doing. So just plugging in 1 here. Okay, so this will give us the square root of 1 minus 2 is equal to 1, and this is not true. So this tells us that this is not going to be a solution. Let's check our next solution here. X is equal to 6. Alright, so this will give us the square root of 16 minus 3 is equal to 1. So 4 minus 3 is equal to 1, which is true. So this tells us x is equal to 6 is going to be a solution for this guy. Alright, so the last two examples in this section are a little simpler. Let's look at 61 here. We're doing something similar. We want to solve for x here, but now in this case we're looking at a third root instead of a square root. The same rules apply though. What we can do is we can cube both sides of our equation to solve for this guy. Now before we do that, we want this radical to be by itself on one side of our equation. So let's subtract 2 from both sides. And so we're left with this. So in order to get rid of this third root, we're going to cube both sides of our equation here. So we're going to get x minus 8 is equal to negative 2 cubed, which we know is the same thing as negative 8. Now solving for x, we're just going to add 8 on both sides of our equation. So x is equal to 0. And so again, we just want to check this guy. We always have to do this when we're using this power rule property here. So we're going to plug in 0 into our original equation here. Doing that, we're going to get the third root of negative 8 plus 2 is equal to 0. Well, we know the third root of negative 8 is negative 2, and negative 2 plus 2 is equal to 0. So this guy is going to be a solution. And then for our last example in this section here, we're given this formula, and what we want to do is solve for this variable m. So let's do that here. The first thing we're going to do is use our power rule here. So we're going to square both sides of our equation. Doing that, we're going to get v squared is equal to 2k over m. Now the next thing we'll do is we'll get rid of this fraction here. Let's move m to the other side of our equation. We can do that by multiplying by m on both sides. Those guys cancel, and we're just left with v squared times m is equal to 2k. Now we want to get m by itself, so we just have to divide by this v squared on both sides to completely isolate our variable m. Doing that, we're going to get m is equal to 2k over v squared, and so this would be our final answer. Alright, so this brings us to section 7.7. So in this section, we learn about complex numbers. So please make sure that you check out the textbook and the lecture slides. There's a lot of important information there. But we're going to start with what's called our imaginary unit I. So I is going to be equal to the square root of negative 1. So in this section, we're now looking at the square root of negative numbers. So if I is equal to this, then this means I squared is going to be equal to negative 1. We saw the power rule property in the last section here. If we were to square both sides of this equation here, we just get I squared is equal to what's under this radical. So that's where we get this. And then the second property here says that for any positive real number b, we take the square root of negative b. This can be rewritten as I times the square root of negative b. And this is because, again, I is equal to the square root of negative 1. So we're going to use these properties here to do question 15. We want to write this as the product of a real number in I and then simplify it. So we have this guy here, and we can rewrite this as the product of a real number in I. We would get minus I times the square root of 144. Okay, so just using this property here. Now we can simplify this because we know that the square root of 144 is going to be 12. So this whole thing then is going to be minus I times 12, which we write as minus 12I. So this would be our final answer here. All right, let's look at these next two examples here. We want to multiply these two radicals. So in this case, since these are both square roots, we can write them under one radical and multiply them. So we have negative 3 times 11, so this would give us negative 33. Now, we want to write this as the product of a real number and I here. We don't want to leave this as just the square root of a negative number. So we'll rewrite this as I times the square root of 33. All right, so let's look at 37. So in this case, we're going to be dividing these two radicals. So the first thing that we'll do in the numerator is we'll rewrite this guy with a positive real number and the product of a real number and I. So in the numerator here, we have this negative on the outside, and then we're going to rewrite this as I times the square root of 64. Doing the same thing in the denominator, we're going to have I times the square root of 16. Now from here we can simplify this. We still have this minus I on the outside, and then we know that the square root of 64 is 8. So let's actually rewrite this as minus 8I. Alright, that's just the format that we like to write it in, is a real number and then I. Alright, so then in the numerator we're going to have 4I. Alright, so then these i's here are actually going to cancel, and then we know that negative 8 divided by 4 is going to give us a negative 2. So that would be our final answer for that guy. Alright, so this brings us to these next set of problems here. So in this case, we're actually working with complex numbers. So I have a little definition here. This is what a complex number looks like. And so this a here is going to be what's called the real part of our number, our complex number. And then bi is the imaginary part. And so complex numbers will be of this form here, a plus bi, where a and b are some real numbers, or a minus bi. So when we are adding and subtracting these complex numbers here, what we're going to be doing is essentially combining like terms. We're going to be adding the real parts together and then adding the imaginary parts together. So looking at 39 here, we have these parentheses around our complex numbers here, but we just have an addition in between them and nothing multiplying them, so we can drop these parentheses here. Now what we have is, looking at like terms here, we have this 3 and this minus 4. So we're going to add those are our real parts. We're going to get negative 1. Now our imaginary parts are 2i and 5i, so we're going to add those guys together. So we're going to get plus 7i. So this would be our answer there. All right, let's look at question 50 here. We're again going to add and subtract our real and imaginary parts. So let's look at what's inside of our brackets here. We want to focus on this guy first. Now we're adding these two complex numbers, and there's nothing subtracting or multiplying anything outside of our parentheses, so we can drop those. Now we're going to add our real parts together and our imaginary parts. So we're going to end up with, inside of our brackets, we're going to have 3, because we have 7 minus 4. And then we have 2i minus I, so this will give us a plus I. Now on the outside of our brackets here, let's focus on this complex number. We have this negative on the outside of our parentheses, so this negative is going to be distributed to both guys here. What we're going to end up with is minus 2 minus 5i. Alright, now we can drop these brackets here, nothing's multiplying them, or we're not multiplying anything on the outside, so we can drop them. So combining our real parts and our imaginary parts, we have 3 minus 2, so this will just be 1, and then we have I minus 5i, so this is going to give us minus 4i. So this would be our final answer for this guy here. Alright, so let's look at the next several questions here. In these cases, we're going to be multiplying or dividing. So we're again dealing with our complex numbers. Now in this case, as we can see for question 57, this 5i is going to be distributed to both terms here. So we can multiply real and imaginary parts, we just can't add them together. So what we're going to be left with here, we have 5i times negative 6, so this will just give us a negative 30i. And then we have 5i times 2i, so this is going to give us a 10i squared. So let's simplify this. We still have this minus 30i here for our first term, but if you remember, I squared, let's write it up here, is equal to negative 1. So this guy here is going to end up being minus 10i. And so, or sorry, minus 10, because we got rid of that I. So this would be our final answer here. And then just writing this in the standard form of a complex number, we would have our real part and then our imaginary part. So this is our final answer for this guy. All right, let's move on to question 60 here. We again want to multiply complex numbers. So this is also just going to be, think of this as two binomials here. So we can use our FOIL method to multiply these guys. So these guys and these and these are all being multiplied. So we're going to have 7 times 3 for our first term, so that'll be 21. Then we're going to have a 7i, a minus 6i, and then for our last term here, this is going to be minus 2i times I, so minus 2i squared. So we can combine like terms and simplify. We have 7i minus 6i, so this just gives us 1i. And then remember, I squared is the same thing as negative 1. So this whole thing is going to be negative 2 times negative 1, which is positive 2. So our final answer in this case is going to be 23 plus I, like that there. All right, and then our last question here, or our second to last question in this section here, we want to divide these guys here. Now, whenever we are going to be dividing complex numbers, what we have to do in this case is multiply by the conjugate in our denominator here in order to fully simplify. So very similar to when we were rationalizing the denominator when we had two terms in our denominator here. So the conjugate of 3 plus 2i is 3 minus 2i. So just like we saw in the last section there, like I said, when we're rationalizing the denominator, we're going to multiply by 1 by multiplying by the conjugate over itself here. So doing that, we're going to have to FOIL our numerator and denominator here. So we're going to have 1 times 3, that'll be negative 3 here. Then negative 1 times negative 2i, so that'll be plus 2i. Then we're going to have 5i times 3, so that'll be 15i. And then our last term is going to be 5i times minus 2i. So this will give us minus 10i squared in the numerator. In the denominator, we're going to do some things similar. These guys are conjugates, so we know some things are going to cancel. But we're going to have 3 times 3, which is 9. And then we have 3 times negative 2i, so minus 6i. And then we have plus 6i, and then our last term is going to be minus 4i squared. So like I said, these are their conjugates, so we know some things are going to cancel. We have that there. In the numerator, we can also combine like terms. We have these two imaginary parts here. Now in the same step, so we have minus 3, and we're going to have plus 17i. And in the same step here, remember I squared is negative 1, so this whole thing is going to become a positive 10. So our numerator simplifies to this guy here, or almost simplifies. And then again here, this is going to turn into a plus 4. So we can combine like terms in the numerator here. We have two real parts. So this is going to end up being 7 plus 17i in the numerator. And in the denominator, we have 13. So writing this as a complex number in that standard form, we're going to have our real part plus our imaginary part here. So this would be our final answer for this one. Now for the last question here, we want to find the power of I for I to the 83rd power. So we're going to do that by using the pattern of I, or our imaginary unit here. So I guess I'll write that down for us here. So I to the first power is just I. We know I squared is equal to negative 1. I cubed is going to be I squared times I, which is going to be negative 1 times I, which gives us negative I. And then lastly, I to the fourth can be written as this here, which is negative 1 times negative 1, which is positive 1. So this is our pattern here. Once we do I to the fifth power, the whole thing repeats because we're going to have I to the fourth times I to the first power, and so on. So we're going to use this to figure out the power of I to the 83rd power. And so whenever we're doing this, we do want to try to break these up into its factors so that some of them are multiples of 4. So what I mean is that we have I to the 83rd power. We can rewrite this as I to the 80th power times I cubed. Now, we know that 4 is a factor of 80, so let's rewrite this as I to the 4th power. And to make this equal to I to the 80th power, we're going to raise this to the 20th power. Okay, so this is exactly equal to this guy here. Just want to emphasize that. We're just rewriting this as I to the 4th power so we can utilize this fact here. So I to the 4th power is just 1, so we're just going to end up with 1 to the 20th power times I cubed. Okay? Now 1 to the 20th power is just 1, and we know that I cubed is going to be minus I. So we just have 1 times minus I. So our final answer for this guy, this fully simplifies to minus I. Alright, so this brings us to the last section we're going to go over in this video. In section 8.1, we're going to look at solving equations using what's called the square root property and completing the square. So again, please check out the textbook and the lecture slides if you haven't done so already. First, we're going to start off with using the square root property to solve each equation here in question 27 and 32. So the square root property says that if x squared is equal to k, then k is going to be equal to then x is going to be equal to the square root of k, or x is going to be equal to minus the square root of k. Now the justification for this property is in the textbook, so again, please check that out if you haven't done so already. So let's use this property here to solve question 27. In order to use this property, what we're going to do is try to get our squared term completely isolated first. So we're going to subtract 7 on both sides of our equation. We're going to end up with 2x squared is equal to 54. Now the next thing we'll do is divide by 2 on both sides to get our squared term, or our x squared completely alone. So we're going to end up with this here. So now we're going to use our square root property. We'll take the square root on both sides here to get rid of this square, to get x completely alone. So doing that, we're going to end up with x is going to be equal to the square root of 27, or x is going to be equal to negative square root of 27. Now from here, we do want to simplify this as much as possible. Our final answer is not going to be the square root of 27 because we can simplify this further by breaking this up into its factors. So we have this here, and then using the product rule here, we know that this is the same thing as the square root of 9 times the square root of 3. The square root of 9 is 3, so we're left with 3 root 3, or negative 3 root 3. So for this example, our solution set is going to be negative 3 root 3 and 3 root 3. So that's how we'd use the square root property in this example. Let's look at 32 here. Now in this case, we have the square of this binomial here, and it's by itself on this left-hand side, so we can automatically take the square root of both sides here. So using the square root property, this means t plus 8 is going to be equal to the square root of 9, or it's going to be equal to negative square root of 9. So we're going to have t plus 8 is equal to 3, or it's going to be equal to negative 3. So now we can just solve for t for both of these equations here. We'll subtract 8 on both sides. This will give us t is equal to negative 5. Or, again, subtracting 8 on both sides, t is going to be equal to negative 11. So in this case, our solution set is going to be negative 5, comma, negative 11. Alright, so for these next two examples here, we want to solve these quadratic equations by completing the square. Now again, please check out the textbook and the slides on this because it is kind of an intricate process, but the whole point is to try to rewrite this equation here so that it's easily factorable. And so we're going to do that by just focusing on the first two terms here. So the first step in completing the square is to just get our terms, our first two terms by themselves. And we also want to make sure when we do this that our equation is in standard form. So we have ax squared plus bx plus c is equal to 0 as our standard form. And then whenever we're completing the square, we want to make sure that a is equal to 1. So those are also important when doing this. So as we can see, the coefficient a here is 1, so we're good. And we want to isolate our first two terms, our squared and our linear terms in this case. Now, the next step after doing that, let's make some space here, is that we're going to add a certain quantity to both sides of our equation. And that quantity is going to be half of our b squared. So in this example here, a is 1, b is 4, and then c, which we moved to the other side, was negative 2. So we want to take half of b squared and add it to both sides of our equations. So b is 4, we're going to take half of that and square it, which is going to give us 4. So what we'll do is add 4 to both sides. Now from here, this becomes easily factorable. This is the product of x plus 2 times x plus 2. And then on the right hand side, this is 6. So like I said, we're completing the square to rewrite this guy in an easily factorable equation here. So this x plus 2 times x plus 2 is the same thing as x plus 2 squared. And so notice that we ended up with an equation similar to what we've seen in the last two examples here. So now to solve for this, we can use our square root property. So we'll take the square root of both sides. We're going to end up with x plus 2 is equal to the square root of 6, or x plus 2 is equal to the square root, negative square root 6. So from here, we just have to solve for x. For both of these equations, we need to subtract 2 on both sides. So we're going to end up with x is equal to the square root of 6 minus 2, or x is equal to minus square root of 6 minus 2. So our solution set for this example here is going to be square root of negative square root of 6 minus 2, and then the square root of 6 minus 2 here. Alright, so that's how we would complete the square with an equation of this form here, where our coefficient a is equal to 1. Now, for this next example here, we're going to look at the case where a is not equal to 1. So, before we do the same process for completing the square by moving the c term over, what we're going to have to do is divide everything, both sides of our equation, by 2, because we need the coefficient of the square term to be equal to 1. So doing that, we're going to be left with k squared, which is what we wanted, plus 5 over 2k minus 1 is equal to 0. Now, from here, we can go through the process of completing the square. We want to isolate our quadratic and linear terms. We want them to be by themselves here. So we'll add 1 to both sides of our equation. Doing that, we're left with this equation here. And remember, we're going to add a certain quantity to both sides. So let's leave a space there. All right, now the quantity that we're going to add to both sides, remember, is going to be half of b squared. So half of b, which is 1/2 times 5 over 2 squared. So this would give us 5 over 4 squared, which is the same thing as 25 over 16. So we're going to have to add this to both sides of our equation. Now, this does seem a little crazy. Maybe it's not obvious right away how we're going to factor this. But notice, in the last example here, we're easily able to factor this, and these two numbers here ended up being half of b. So that's what is nice about completing the square. Whenever we're going to factor something of this form here, where this last term is half of b squared, whenever we factor this, we're going to end up with a binomial of this form here. It's going to be our variable plus half of b, which is 5 over 4, squared. So we're going to have k plus 5 over 4 times k plus 5 over 4. And then on the right-hand side, we're going to have 25 over 16 plus 1. So this would give us 41 over 16. All right, so this is the same thing as k plus 5 over 4 squared. So this tells me we can use our square root property here to solve for k. Doing that, we're going to have k plus 5 over 4 is equal to the square root of 41 over 4. Since we have the square root of 16 in our denominator here, that'll give us 4. And then we also have that this guy is going to be equal to the opposite of that. So from here, we just have to solve for k. So for both these equations, we're going to subtract 5 over 4 on both sides. We're going to get that k is going to be equal to this here. And actually, we can write this over one denominator since we have a common denominator. So minus 5 over 4. So this is going to be our solution for this question here. And we found that by completing the square. And again, when we're completing the square, I just want to emphasize here that this quantity is going to be half of our b term here. So it's always going to be this guy. And we just want to be careful of our signs too. If b is ever negative, then we're just going to have negative for this guy here. And again, I just want to emphasize here that this term, when we factor, is going to be half of our b coefficient here. So this guy is this guy here. And so that's the whole point of completing the square, so that we can easily factor this here. And this will always be half of our b term every time we complete the square. All right, so let's look at the last two examples in this section here. For 83, we want to solve this equation here. So we're going to use our square root property. The only thing in this case is that we're going to end up with complex solutions. So let's take the square root of both sides. Since we're taking the square root of a negative number, that already tells us we're going to end up with some complex solutions. So we're going to have 6k minus 1 is going to be equal to the square root of negative 8, or it's going to be equal to negative square root of negative 8. Now from here, let's first rewrite this with our imaginary numbers here. So we're going to have I times the square root of 8, or negative I times the square root of 8 here. All right, so from here, we're just going to solve for k. So the first thing we're going to do is we're going to add 1 to both sides of both of our equations here. So we're going to have 6k is equal to I times the square root of 8 plus 1, or this here. Now the last thing to do to completely isolate k is we're going to divide by 6 on both sides. So we're going to have this guy divided by 6, or this guy divided by 6. All right, now from here, there's a few things we can do to fully simplify this. First, let's try to rewrite the square root of 8 here. Let's simplify this as much as possible. We know the square root of 8 is the same thing as the square root of 4 times 2. So this is going to be our answer for the square root of 8. So running out of room here. We're also going to rewrite these guys so that we have our real part plus our imaginary part. So we're going to end up with k is going to be equal to, for this first guy here, our real part is 1 over 6, and then our imaginary part is square root of 8 times I, which is the same thing as 2 root 2 times I over 6. And then our other solution here is going to be our real part, 1 over 6, and then plus our imaginary part. So this is going to be minus 2 root 2 times I over 6. So this would be our solution for this one here. And so as you can see, our answers are complex numbers. All right, and then the last question we're going to look at is a word problem here. We're told that the Gateway Arch in St. Louis, Missouri is 630 feet tall, and we want to determine how long would it take an object dropped from the top of the arch to fall to the ground. And what we're going to use is Galileo Galilei's formula, which says that d is going to be equal to 16t squared. So in this formula, d is going to be the distance. So if we were to drop something from the top of this 630 foot tall arch, that means the distance from the top all the way to the ground is going to be 630 feet. So all we have to do is plug that into our formula here. We're going to have this is equal to 16t squared. Now the whole point of this question, we want to figure out how long it would take. So we're trying to find t, we're trying to solve for t. So we're going to use our square root property, but the first thing we're going to do is completely isolate our variable here. So we're going to have 630 divided by 16 is roughly 39.38, rounding that. It's going to be equal to t squared. So solving for t, we're going to take the square root on both sides. So this means t is going to be equal to the square root of 39.38, or t is going to be equal to minus that. However, in this question, we're looking for how long it would take for this an object to fall to the ground if it's dropped from the top of this guy. Now, so this is our time in, let's assume seconds for this question, and we can't have negative time. So that means this guy is not going to be a solution because we can't have negative time. So in this case, this is our only solution here. So taking the square root of that here, this will be about 6.28 seconds. So that's how long it would take to drop something from the top of this arch here. All right, so that'll be it for this video.